Hey, welcome back. So this is part 2 of a simple harmonic motion lesson that we're doing, and so this is the Hooke's Law example problem that I want to go over next. That builds on my previous work. If you haven't seen my previous screencast on this, I'm going to put a link in the upper right so you can take a look right now. Alright, let's get to it. So let's take a look at this problem. Now we're going to do a vertical problem here. So we have a relaxed spring that's at equilibrium right here, and then we attach a mass of 0.75 kilograms. The spring gets stretched down, it vibrates back and forth for a while, but because it's in the real world, it does lose some energy and eventually comes to a stop. And that's what we want to take a look at. What is the equilibrium constant of the spring in newtons per meter? Alright, well, one thing I can do is write down my mass here, and if I write down my mass, I can give myself some more room to work with. I'm also using my preferred equation here, so next up, I'm going to draw my free body diagram. This is where things get a little complex. Of course, gravity is pointing in the down direction. We'll call that negative, and the up direction we'll call positive. In this case, our restoring force is going to be upwards. Why is that? Well, it's the negative direction of the displacement. So the displacement is down. Over here, it's been pulled down from this equilibrium position. And so the restoring force is pointing upwards. Okay, well, if that's the case, let's go ahead and build on strategies we've used in the course so far. Let's do the sum of the forces strategy here and see what happens. And this is going to be the trickiest part of the entire thing right here. Again, I'm going to call this a negative FG or a plus negative FG because I'm just saying the sum of the forces are, and then I add up literally the sum of the forces. Next up, I'm going to write Newton's second law, where I say the sum of the forces is also equal to mass times acceleration in the y. My question to you is this object accelerating in the y-axis when it comes to a stop here? The answer is no, it's come to a stop. So it's not even moving, let alone accelerating. And so if that's the case, then this whole term drops out. We can set these two equal to each other, but that just means Fs plus minus Fg is equal to 0, and I can isolate for them. Now this next step may be confusing to folks. If you take a look at this, I'm going to call it K delta x, not minus K delta x, but K delta x. Let me talk about why that is. We have already incorporated the spirit or the actual physics of this negative sign, you could say, because we said, well, the displacement is downward from this position to this position. The displacement has been downward, right? And we said, well, then the Fs must be upwards because that's what this negative sign here means. It's in the opposite direction of the displacement. Well, if that's the case, we've already used that negative sign once. We don't want to use it a second time. That would be giving it double its weight in importance, you could say. And so we're going to leave this as a positive value because it's now heading upwards, and we've already signified it's in the opposite direction of gravity. So now we can go ahead and isolate for our unknown, which is K, plug in our numbers at the very end, and solve. We end up with that answer in newtons per meter. And if you think about that, hopefully that makes sense. For every meter you compress or stretch a spring, you have to exert a certain number of newtons. And that's how you handle Hooke's Law problems and what the basis of simple harmonic motion is all about. So hopefully this has been helpful. Please stick around. I'm going to do more lessons in this unit we're doing of vibrations and waves. If you have any comments, please let me know down below. And I hope you have a great day. Take care.